Hello, good morning. So this is the award session. We are going to have the presentation of the awards for the young scientist physicist, and also later the posters awarded by ICHEP that were presented this week. Before that, Professor Shellman will talk about the C11 report from IUPAP.
I can hear myself. Okay, so I am going to sort of go through the C11 summary rather quickly because you want to hear from the wonderful award winners, not from me. So here we are, the C11. I would just like to start out by thanking our hosts here in Seoul as the local organizing committee, who are pictured here in a picture I think that came from Freya Bleckman. I found it on the web. You guys are famous now. Okay, the many dedicated staff members. As you've noticed, there's been a huge number of very good staff members here. The strong support we've seen from the Korean physics community, and the strong support from the Korean politicians and industry, as indicated by the great talk we had last night, and the wonderful Korean culture presentations that have been part of the conference and the banquet. If you missed the banquet, you really missed something. So here's the C11 membership if you want to complain to one of us. We don't actually represent countries, we sort of represent the world, but here's a list. There's the officers, we serve for 3 years, and then there's the members of the committee who come from, we lost our Ice Cube person, so we don't actually have all 7 continents right now. So what we do, the main activity of C11 turns out to be the supervision of international conferences such as this one, but we also supervise the International Committee on Future Accelerators. We have done reports. If the world needs a report on some major pressing issue like authorship or large collaborations, we've done that. Over the last 2 years, we've been arguing with the higher education ranking organizations over their plan to drop all large collaborations, meaning Atlas, CMS, DUNE, and LIGO, from any university rankings. I think we've reached a compromise with them on that, which doesn't give you full credit for all 1,000 papers, but large fraction of the things. And the Young Scientist Prize, which is awarded every 2 years at ICHEP, and we'll be doing that very quickly. Okay, I'd just like to add that it's an international body. It has very, very formal guidelines, so I'm going to summarize them here. The major thing that's been something we've done since the very beginning is ensuring the free movement of scientists and opening access to science to everyone. And as time has evolved, people have begun to realize that involves things like gender and minority status and a much larger number of countries than just the ones that we started out with. So that's as we've evolved, we've paid more and more attention to those issues, and even more recently, the move to make certain that there's no harassment, that everybody feels comfortable at conferences and other physics gathering. So these are things that are part of the mission of IUPAP, and it's also part of what we ask conferences to keep records on and report. So we provide advice on this, and we also require reporting as part of our sponsorship of the conferences. So another new thing for IUPAP is that we have been asked to create a neutrino panel, which will serve over the next 3 years. ICFA had already had a very successful panel on accelerator-based experiments. But if you looked at the neutrino sessions here, only about 1/3 of the neutrino talks here at ICHEP were actually based at accelerators. So this panel is going to try to span the full range from astrophysics to nuclear physics to reactors to the particle accelerator-based experiments. And right now the panel is in the process of formation, and Nigel Smith, Takaaki Kajita, and Manfred Lindner have agreed to chair this, and you'll be hearing more from this committee for input and meeting the members reasonably soon. Okay, so our meeting here was mainly conference organizers. One of the things we do have is we now have written guidelines on how to apply to host a conference and what is expected, which are on the C11 page. And I'll just point out that there are several types of conferences. There's A-type conferences, you're in one. There's only one of those a year. It's like ICHEP and lepton photon. There's B, which are substantial, but somewhat topical. For example, LHCP or neutrino. And C would be smaller, regional, or special. There's also a possibility of getting an endorsement for IUPAP, and the reason you might want sponsorship and endorsement is not just to have us interfering in your business, but it also helps you obtain funding from your national agencies, and often is very useful in trying to get visas. If a conference is endorsed by IUPAP, then it's much easier. Your invitation letter will be taken much more seriously than it might be otherwise. There are fake conferences out there, so always look for that IUPAP label on your conference. So I'd just like to, we had a very great summary on ICHEP 2018. There were 1,160 participants. This is a very large attendance for one of these conferences. It's typically somewhere between 800 and 1,200. There have been more, but it's actually quite rare. 105 travel grants were given. But one of the things that the conference organizers have done is they've actually reported on the demographics. They can tell you where people came from. This time around, dominated by Asia and the Pacific, but with growing participation from Africa and sort of a balance of less people from the Americas than I would have expected. The gender balance for the attendees and is actually, if you saw the talk about diversity studies from Atlas, it's basically what you would expect for a typical high-energy physics experimental collaboration. In fact, the younger end of that. So those are the kind of statistics we look for, and this is what you would expect given people applying to a conference. And registration category, students made up more than 25% of the registrants, which is great, and that reflects the help that has been given to students. The same categories are done for conveners and for plenary speakers, and you can see that, in fact, reasonable balance has been achieved between them. I might notice that Europe actually has many more plenary speakers than it did attendees. But so I think the conference organizers are required to do these reports, and it's very useful to have this information. Okay, so future conferences, just some ads. So at this meeting and previously, we review conferences, we get reports. So the conference scheduling is that ICHEP is in the even-numbered years and lepton photon is the odd-numbered years. They tend to rotate between Asia, Europe, and the Americas. It turns out they rotate in opposite directions, which leads to some strange things. We actually don't know where ICHEP 2022 and 21 are going to be, and I'll be discussing that later. But here's what's coming up. So at the end of in September, actually, the Baldin Seminar, which is, this is going to be its 49th anniversary. We're probably hoping to celebrate the 50th in 2 years. It will be held at Dubna in Russia, and this specializes in QCD, relativistic heavy ion collisions. So that's coming up very soon. Lepton Photon 2019 is going to be in Toronto, and I'll just point out that there's going to be a slight change. They're actually going to start including parallel sessions. Lepton Photon has always been all plenary, and we believe that that actually hurts attendance because it basically gives young people no possibility to do anything beyond a poster. So they're actually going to be adding parallel sessions. And I might add that every time people hear it's going to be in Toronto, they get very enthusiastic. So we're hoping to see huge numbers of you there next year. LHCP, which is a Hadron Collider experiment, is actually going to be held in Mexico, in Puebla, Mexico, in May of next year. So this is another conference that rotates around the world, and next year it's going to be in Mexico. And finally, and last but not least, I guess, is that ICHEP 2020 will be in Prague, 30th of July through the 5th of August, and we're looking forward to seeing all of you there. And I think that, that's fine. And finally, we are actually going to, instead of basically having people show up at this meeting, we're following what EPS does. We're actually opening up a formal solicitation process for the conferences. So we have the guidelines. I can show this up here. The guidelines are actually written down here for the conference guidelines, but basically we're looking for hosting opportunities for Lepton Photon and the Rochester conference. People should contact me, and we're going to be accepting written applications until November 1st. The application basically needs to contain information about the participating institutions, the local organizing committee, likely costs and locations, and alternative funding sources. And we would be making a decision based on the written input by the end of 2018, because people need a large lead time. You don't just get I'm sure these guys were already arranging to use this building before it was built. So it is important to get things going early on. So with that, I'm done with my talk. If people have any people have questions about this part of the talk, now might be a good time to ask them. Okay, with no questions, I would like to invite our prize winners up here, and they're going to be presented with a certificate, a medal, and I hope that they have already received, I think it's 1,000 euros in their checking accounts. So I would just point out that this is every 2 years, and we actually had 63 nominations. So these people are the best of the best. So our winners are, first of all, is Yaroslav Trinka from the University of California at Davis for the discovery and exploration of new physical and mathematical principles underlying the dynamics of particle scattering amplitudes in a wide range of theory. Yaroslav, are you out there? Yay! Okay, so thank you. There's your medal. Congratulations. And you get a certificate. And flowers. Unfortunately, you don't have 3 hands. There's actually a box that goes with this. So. And Yaroslav will be giving his talk in a few minutes, but we're going to do the awards first. Okay, so our second, oops, oh wow, cool. Our second prize goes to Heather Gray from Lawrence Berkeley Laboratory for her broad and creative contributions, as well as leadership in performance and physics analysis in the ATLAS experiment and beyond, culminating in her strong role in the searches and initial measurements of Higgs boson interactions with quarks. So Heather, congratulations. Okay, so, oops, are we in the right place? Okay, so here's your medal. And signed by me. So, congratulations again. And flowers. Okay, I will now disappear, and Yaroslav will take over with the first of the 2 talks.
Okay, it's a great honor to get this reward and being able to speak at this wonderful conference. So this will be a theoretical talk, and I will tell you something about new insights and new methods how to calculate scattering amplitudes in quantum field theory. And for me, the particle experiments is a probe to fundamental laws of nature. And as a theorist, my question is, what happens during the scattering process of elementary particles? How can we understand that block when particles go in and some particles go out? And there is a canonical answer to that, developed by Feynman and others in the 1940s, and that's that inside a blob is a sum of Feynman diagrams. We have to calculate in quantum field theory using the rules we learned in the grad school, and that's, in principle, the answer to that question. However, in last years, we've seen that at least in certain cases, there is an alternative answer to that question, which gives exactly the same result, and it's related to geometry. So the same thing that we get as a sum of Feynman diagrams can be also obtained as a volume of some geometric object. And I try to give you at least some flavor of what this is about. OK, so scattering amplitudes, the thing I'm interested in, are mathematical functions which gives us the probabilities of outcomes of scattering experiments. And for example, in the context of the quantum chromodynamics, it's important to calculate these functions to high precision in order to be able to distinguish the QCD background from the new physics. And at high energies, if we scatter protons, the dominated interactions are gluonic interactions. So we can calculate gluonic amplitudes, and then we have to do further work and add Parton distribution functions and more work to actually turn it into the protonic scattering. But for me, the gluonic amplitudes is the object of interest. And people already did these calculations a long time ago. And in early 80s, there were plans for new supercolliders. And people started to do these calculations in the perturbation theory, at least in leading order. And the status of the art in early 1980s was the calculation of the 5 gluon amplitudes, 2 go in and 3 go out, using the standard methods of QCD and Feynman diagrams. And the brute force calculation gives these results. It's 24 pages of algebra like that. If you just do the straight calculation of Feynman diagrams, when these tiny things on the slide are just the dot products of momenta and polarization vectors. So this looks very complicated, but it was needed at that time. And the next process on the list was 2 gluons going to 4 gluons, so the 6-point calculation. And this was done by Park and Taylor in 1985, and it was needed to calculate 220 Feynman diagrams, and it was roughly 100 pages of calculations, which I showed on the previous slide. And in 1985, they wrote a paper after they finished the calculation, which name is just gluonic 2 goes to 4. They just gave the result of that calculation, and using some smart notation and some fake supersymmetry they used in that context, they were able to compress the result into 14 pages, and that was the 14 pages. That's basically the whole paper. Now, in the outlook of this paper, they write that furthermore, we hope to obtain a simple analytic form for the answer, making our result not only an experimentalist, but also a theorist delight. So it's not clear what they meant when they look at these 14 pages, but what happened in the next year, that they realized that these 14 pages can be compressed into a single line formula, known today as Park-Taylor formula, when these brackets are dot products of so-called spinor helicity variables, which are related to the momenta of particles. I will not go into the details. Here is the definition on the right. But maybe more familiar would be if we write the square of the amplitude. That's just given by the dot products of 4 momenta. So the result was surprisingly simple, and there was no explanation at that time why this very complicated calculation led to this very simple result. Now, if we see formula like that, from just the mathematical structure, we can guess what would be the endpoint generalization, and they indeed did it, and wrote a paper, Amplitude for N-gluon Scattering. This is for a particular helicity component of the gluonic scattering. And it has this simple form, and in order to get it using conventional methods, one has to sum, in principle, infinite number of Feynman diagrams if you go to large N point scattering. OK, so there was after this discovery, people tried to understand more where does this simplicity come from and how to use it in doing calculations. And the question posed is, what is exactly the scattering amplitude as a final result? And one side, we can calculate it as a sum of Feynman diagrams. But on the other side, we would like to think about it as a single object, not as a sum of some pieces, but as a single object. And this idea of an amplitude being fixed completely by some physical properties actually goes back to the 60s, to the analytic S-matrix program. But the modern methods for amplitudes actually use both sides. On one side, the perturbation theory, the fact that there is an expansion using Feynman diagrams. And on the other side, the desire to calculate the amplitude directly without going to any expansion. And the lesson from the Park-Taylor formula was that the simplicity reveals if we work with on-shell gauge invariant objects rather than with individual Feynman diagrams, which are off-shell and not gauge invariant. And also, the simple expressions are obtained for helicity amplitudes when we fix the helicities on individual gluons. For example, the formula I showed on the previous slide, so-called Park-Taylor formula, corresponds to 2 negative gluonic helicities, and the rest are positive. And new efficient methods were developed. After that, I just mentioned two here, unitarity methods developed by Bernd, Dixon, and Kosover in early 90s, and they are actually used also for the calculation of the QCD background in so-called black hat collaboration, and also other method which applies to 3-level amplitudes. It's recursion relations, found in 2005, and the idea is build the higher point amplitude from lower point, and this way of doing that is extremely efficient, as you can see from the comparison between the number of Feynman diagrams and the terms in these recursion relations for some particular processes. So calculating and studying scattering amplitudes became a new field. We have now annual conferences, which was just a few weeks ago this year at SLAC, and also summer schools for students who want to enter the field. But there are 2 major motivations why to focus on scattering amplitudes. One of them is find some efficient ways how to calculate amplitudes, which can be then further used in particle colliders to calculate QCD backgrounds and other things. But the other motivation is use amplitudes as a probe to study quantum field theory in general, to find new structures. And this is basically my motivation. So in what I tell in the following, I cannot claim that this is useful now for doing any calculations, but potentially the goal would be to make it efficient tools. Okay, so there is even a much bigger goal than just studying scattering amplitudes, and that's to find some new formulation of quantum field theory, at least in perturbation theory, where the picture of particle interactions in space-time doesn't make any direct appearance. And I will explain what I mean by that on the next slide, or at least the evidence for that we have now. And hopefully this new formulation would make the calculation easier eventually. But the deep motivation why we would like to find it also comes from gravity, because the quantum field theory has the notorious problems to incorporate gravity. And if we have another formulation, this might put us in the better place to do this next step. And we don't know if this formulation exists or not, or how it looks like, but we have one particular example when we can calculate amplitudes in a completely different way, which doesn't look like particles, interactions, or fields. And it's in one example, but it can give us the hint how to continue further. And this one example we called amplituhedron. The idea actually comes from an early observation of Andrew Hodges in 2009, when he studied some 3-level amplitudes of gluons using new kinematical variables called momentum twisters, but in principle it's just some change of variables from momenta and polarization vectors to some 4 vectors z's. And he used these recursion relations to some particular gluonic process, and in these recursion relations you get just only 2 terms. These are the formulas that are represented. You can rewrite them back in the momentum space if you want. It's just some kinematics. But the crucial observation was that for each of these terms, you can interpret them and represent them as volumes of some tetrahedra. And the amplitude is a sum of two of them. Each of them is individual tetrahedron, and in each term there is one spurious pole, which doesn't correspond to any physical factorization, and once you sum it, the pole cancel, and the amplitude, the tree-level amplitude with this particular helicity combination of gluons corresponds to a volume of polyhedron. And Feynman diagrams give another triangulation of the same object. The amplitude is this volume, and you can represent it any way you want, indeed. And all answers are correct, but the amplitude is a single object from this point of view. And the amplituhedron is basically the generalization of this idea, which was established for all tree-level amplitudes for gluons. The amplitude is a volume of some object. The positions of vertices of these objects are given by energies and spins of particles. Once you have that, you can build this geometry, you can calculate the volume, and it gives you the same answer as the sum of Feynman diagrams at leading order in perturbation theory. The geometric object is not it's not just polyhedron, it generalizes to some much more curvy space called positive Grassmannian, which is the space which was recently studied by mathematicians in the literature, which is a very interesting historic coincidence if you think that the progress in mathematics happens at the much larger time scales. People studied these objects just in the last 10 years. If they didn't, we would probably not find it. And the full definition of the object fits on one slide, but the details are not important here. Now, for loop amplitudes, which is the most difficult part, of course, we don't know how to do it in the QCD yet, but we know how to do it in a toy model for QCD, which is called planar n equals 4 super Young-Mills. It's a maximal supersymmetric extension of the Young-Mills theory, and in a very precise sense, it's an analog to integrable models in classical mechanics, like Kepler model, or in quantum mechanics, like hydrogen atom. It has some hidden symmetry, some analog of Runge length vector, which simplifies dramatically the calculation. So it's different than QCD, but it has many features of QCD, and this is where we found the formulation of the amplituhedron, where we were able to make the progress. Now, in this picture, calculating amplitudes is reduced to the math problem of calculating volumes of certain geometric object. It's not an easy problem, but it's a different problem. It doesn't look like scattering of particles. It's a math problem of finding volume, of triangulating some geometric space. We cannot derive this object from just from Lagrangian or quantum field theory, because it doesn't use any language of quantum field theory. But what we can prove is that the volume of this object gives exactly the same function as the scattering amplitude calculated using Lagrangians, Feynman rules, and Feynman diagrams. It's the same function. And there are several steps one has to prove, but the main ingredient is that the object factorizes correctly. So in this very specific case, we achieved the goal of finding a new definition for the scattering amplitudes, which makes no direct reference to fields and particles and Lagrangians. So this is just very first step in a long program, and maybe this is very special, and no reformulation of QFT exists in general, and maybe it exists and looks differently. We don't know, of course, but at least we have to start. And here, in studying scattering amplitudes from this perspective, there is some internal notion of doing something right or wrong, because we can always calculate the amplitude using the standard methods, like Feynman diagrams or some more modern methods like recursion relations, and obtain theoretical data, analyze them, look for new structures, and then make a proposal for some other method how to do it, for example, for this geometric method. And once we have it, it must give predictions. It gives predictions, we calculate, and we must compare. It either works or it doesn't. If it doesn't work, the idea is wrong. If it works, we can proceed. And of course, there are many steps in this process we have to now do and try, there is no guarantee that anything would work. We have to add masses, quarks. We have to finally do the loop amplitudes in QCD, understand the renormalization, standard model, and so on. And in the end, one would like, if it exists, such a reformulation to establish it as an efficient computational tool. But let me just conclude that it's interesting that for this, there exists an alternative picture for the dynamical particle interactions in 4 dimensions, either experimentally, directly what is measured at colliders, and theoretically presented by Feynman diagrams, and at the same time, at least in some specific case, 3-level amplitudes in QCD and loop amplitudes in some toy model for QCD, you can represent the same thing by some static geometry in high-dimensional space, when there are no particles and no interactions. You have just to calculate some volume of some object. OK, thank you very much.
Thank you very much. So we have time for one question. Quick.
How can you equate a complex scattering amplitude to a scalar quantity such as a volume?
So the amplitude is for the particular helicity configuration. So you fix the helicities of your gluons. So we are able to do it just in the context of gluons at the moment. And you fix your momenta and polarizations. So you get some rational function of momenta and polarizations. And so this is some function. And the claim is that the same function is given also by this volume. The positions of vertices are directly related to these momenta and polarizations. So the volume function is some rational function on this kinematical configuration. And the claim is that exactly produces the scattering amplitude. So the function can be complex or real, depending if your momenta are real or complex, or which kinematical variables you use. So more precisely, these kinematical variables we use, these z's, these momentum twisters, are in general complex. So we get some complex function, but it then translates to some real function in terms of momenta. Now, the other challenge is to do it for the loop amplitudes, when it's not just rational functions, but becomes a transcendental function, or in general, even more complicated function of the kinematics.
So thanks, Jaroslav, and congratulations. So we'll welcome now.
Good morning. I'm humbled to be standing here to have received this prize, and I would like to spend a little bit of time showing you selected topics from things where I've either worked directly or had a significant role, for example, as a convener. And this will actually cover a variety of topics, and I'd like to sort of try and tell you a bit of a story, starting from the Atlas pixel detector and ending with one of the results that has been highlighted a lot in this conference, which is probing the coupling of the Higgs to quarks. So when I joined Atlas, which was now quite a while ago, more than 10 years, I worked on the calibration and commissioning of the Atlas pixel detector. And so you can have a look either at the sketch, showing the detector here, or you can actually have a look here at the real detector before it actually went inside Atlas. Now, once we received the first data from the LHC, the first thing that we wanted to check was to see if this Monte Carlo simulation of the detector, which we'd been working on for many years, actually described the data. And so what we did is we had a look, and we compared the number of hits that we saw in the pixel detector between data and simulation, and we were pleasantly surprised to see that we had this really excellent agreement between the two of them. Of course, not everything was perfect, and as we started to get more data and do more detailed studies, we started to probe whether the amount of material we had in the detector was really accurately described. And to do this, there's a figure here to illustrate. We had a look to say, if we had a track in our pixel detector, did we actually see it in the next detector moving out? And you can do the same thing in data and simulation, and what you can see is that not necessarily everything is perfect. In fact, this is actually the plot that you get after we'd done the studies and identified and fixed some of the issues in the material, and we've been working on this since then. Now, all of these components of sort of understanding the detector, understanding the track reconstruction, were really critical in the first paper that came from the ATLAS experiment on data, which was a measurement of the charge particle multiplicity. Actually, we've seen quite a lot of that this morning, mostly in the context of heavy ions. And what I'm showing you here is really the summary plot we have from ATLAS, looking at the average number of charged particles at central pseudo-rapidity as a function of different energies, also as a function of different momentum cuts and number of charged particles. And what you can see here is the models that we use today, where there's quite a range of variations, but overall there's quite good agreement. Now, understanding this is not only important in terms of understanding the physics of these soft interactions, but given that we have so many additional proton-proton collisions at the LHC, we really do want to make sure that these are all well modeled, as these form backgrounds to further studies of physics. Now, I said I'd come back to the material, and I couldn't resist but to show you this picture. Actually, it's not a picture. This is data. What we're showing here is actually a map where you can really see the elements of our new detector we added for run 2, which is the IBL, and new innermost pixel layer. And you can actually see here the individual modules mapped out by the location of hadronic interactions with the detector material. We use this, and also the rate of photons converting in the detector material, to actually set systematic uncertainties on our material description, and we're actually well within 20% now in terms of our overall description in all regions. Now, adding new detectors typically can bring new challenges, and what we found with the IBL, which we found is that when the temperature of the staves changed, it actually ended up bowing. And this is what the plot's showing you. It's for various different temperatures, the amount of bowing that one had on the individual detector staves. Now, when we started seeing the performance of the detector in beam, what actually happened is that some radiation effects induced currents in the modules, which actually changed the temperature. And what we found is that run by run, this is what you see here, there was actually movement, which was coming from the same effect. And so what we did is we developed a very fast alignment procedure to actually correct for this on a run-by-run basis, such that there was no degradation to any of our physics performance. Now, one of the topics that's quite currently quite much attention in particle physics is sort of looking into booster topologies or high-PT jets. But however, when you actually go inside a jet and you start looking at the separation between tracks, what you find is that very quickly you actually end up getting tracks where the individual energy deposits in the detector overlap, such that you can't resolve them. And this really limits your ability to actually study the properties of these jets. It's kind of illustrated in that sketch over here. So what we did is we implemented a neural network to use the charge information from the pixel detector to actually identify and split these clusters. And this is what you can see illustrated here. The original distribution where you can see the double peaks from an unresolved cluster has been resolved after using this neural network clustering algorithm. Actually, this improved our overall impact parameter resolution and also improved our tracking in the center of jets, such that we ended up with much better tracking in jet cores. Now, moving on to the Higgs, as you've seen in many talks this week, the Higgs was originally discovered via its decays to bosons. And if you look at the Lagrangian, the fermionic couplings are added by hand, and of course not necessarily needed for electroweak symmetry breaking. Of course, I view this as an opportunity, and I think it makes it particularly interesting to really study the Higgs coupling to quarks. Now, there are two ways you can go about it. Back we go. One is looking at indirect methods, for example, looking at the loops in gluon-gluon fusion or Higgs to gamma-gamma, and this was already done at the time of the discovery. But of course, if you're interested in new physics and wonder if there might be contributions, one wants to also look at direct probes. And the three I'd like to sort of talk about today is talking about Higgs to BB decay, a little bit about Higgs to CC, and then also about TTH production. Of course, there were many more details in talks this week, and I will not be able to go into them in the same level of detail. Now, looking at the picture that we had back at the end of run 1, where it's summarized in this very nice plot, which shows the strength of the coupling as a function of particle mass. And what you want to look at, of course, is the size of the error bar to see how well we were doing experimentally. Overall, and if you can kind of turn it into ratios for each of the different couplings, we saw very good agreement with the standard model. However, if you look a little bit more closely, you actually see that we had much better precision for bosons than fermions, and indeed, we actually had no direct evidence for the coupling of the Higgs to quarks. Now focus a little bit on the coupling of the Higgs to top quarks. As I mentioned, we had indirect constraints on the order of about 15% at the end of run 1, but we do want to really look at this direct production to be able to probe for any new physics contribution. It's a tough channel. The cross-section is tiny, about 100 times smaller than gluon-gluon fusion, and to do it, you actually need to combine information from multiple top and Higgs decays. And so what we've done in ATLAS is we've used 4 analyses to probe it, so gamma, gamma, ZZ, BB, and multi-lepton. Multi-lepton's the one I'm going to talk about, and this is actually, you can think of it as mostly a combination of WW and tau tau. And of course, as we have top quarks around, all of these channels also include at least 2 B jets from the top decay, meaning that the role of the pixel detector is really particularly important. In this TTH multi-lepton analysis, what we do, as is done in many Higgs analyses, is we define categories. These are based by just counting the number of like leptons, electrons or muons, and hadronic taus. Trigger events by a combination of single or dilepton triggers. We require at least 1 B jet, and between 2 or 4 jets, depending on the channels. Now, as there's actually quite a lot of background around, and we really want to get as high precision for the signal as possible, we use boosted decision trees to extract this TTH signal from the backgrounds. And there are actually a number that are important, things like TTW, TTZ, diboson, and TT bar. In the 3-lepton channel, we actually used a fairly novel technique from machine learning, which is called a multinomial BDT. And I've tried to illustrate it with a sketch here. I think I probably failed, because it's actually 5-dimensional. And the idea of this is to actually simultaneously extract the signal while defining control regions such that you're able to study your background. And it's a bit hard to see here, but if you look at these boxes that I've made in red, these are actually showing you the final 5 control regions and signal region defined, and actually which processes contribute to each of those. On this slide, I want to talk a little bit about some of the challenges. In all of these analyses, there are actually many challenges. One of them is trying to find the signal where we have backgrounds that have only been studied to a very limited extent so far. And so, of course, you do not want your result to depend too strongly on what assumptions you actually make about the backgrounds. And so the example I want to show you here is that based on these control regions, which I introduced in the previous slide, we can actually run a cross-check of the analysis where we actually allow it to determine the cross-section for TTW and for TTZ. These are the mu values. So of course here we are looking for 1 to see consistency with the standard model. And this is what we see. And so what we actually see is that our Monte Carlo predictions are indeed accurate for these processes, given the uncertainties that we have at the moment. Another challenge are the backgrounds from non-prompt leptons. These tend to be a mixture of either B-quark decays or from photons passing through a detector material, converting and looking like an electron. And these, we don't necessarily trust our simulation. So we determine them from data, from control regions, and then extrapolate them into our signal region. And this is just a plot that's showing you the PT of a lepton. And what you want to see is you want to see this big purple component, and you see that it dominates in this validation region, showing that we had overall a very good description of this challenging background. I do want to show you this plot. This is actually showing you some of the different regions, again, in the analysis. And as I mentioned, it's mostly B quarks. This is the red. But we actually also had this significant background from photon conversions. And for this, we actually use the input from the measurement of the detector material to really set the scale of our systematic uncertainties. So kind of putting it all together on this slide, I want to show you the 2 distributions. These are from the TTH multi-lepton analysis. And so this is the signal region for 3 leptons, signal in red, backgrounds in colors. And from the 2 lepton, same sign. These are the 2 most powerful channels in the analysis. And what we had is an expected significance of 2.8 sigma and observed significance of 4.1. Now, more recently, just this summer, this analysis has been put together with all the other TTH analyses into a combination. And from this, we obtained an expected significance of 5.1 sigma and an observed significance of 6.3 sigma. So from the top quark to the bottom quark, this one is the decay channel, which has the largest branching ratio. But despite this, it's actually extremely challenging due to large backgrounds. So far, ATLAS has probed VBF, VH, and TTH production, but the most powerful channel that we have is indeed VH. Here we have 3 channels, which we characterize by the lepton decay, so of the vector boson. So there's the 0 lepton channel, the 1 lepton channel, and the 2 lepton channel. And we trigger these events by using a mixture of lepton and missing energy triggers. Again, we require 2 B jets and use a BDT to extract the Higgs from the large B plus jets and TT bar backgrounds. Here you can see an example plot. This one comes from the 1 lepton analysis. And again, here you can see the signal in red, and you can see the large backgrounds, TT bar in orange, and the B plus jets in green. There's also a complex profile likelihood fit, which we use to extract the signal while we're actually making sure to estimate the normalization of our backgrounds. Again here, the challenge, you might have guessed from what I was saying, is the backgrounds. And this is something we were actually aware of already early on. I want to show you this plot. It's actually back from 2012 and uses only 35 inverse picobonds of data, which is a tiny data set now for the LHC. And what we did is we actually measured the W plus B jet cross-section in various bins, and we found that the Monte Carlo that we were using at that time actually underpredicted what we saw in data. It's been an ongoing story of improvements in the Monte Carlo and improvements in the analyses. However, when we did the analysis back in 2014, what we did is we decided to do control regions to actually check the modeling of the Monte Carlo. And this plot here is showing you the delta phi distribution between the 2 jets. So these would be your Higgs candidate jets, compared to data and simulation. And what you can see is that they actually don't agree very well at all. Indeed, there's actually this strong slope. Similarly, and I think this was mentioned already in the top plenary, there is this issue that the top PT is actually not modeled particularly well. And the challenge here was to be able to try and do this analysis where you're looking for a tiny signal over these backgrounds where you really don't have a good description. And actually what we did is we used these distributions to actually obtain corrections we applied to the Monte Carlo and uncertainties to be able to do the analysis while we wait for our theory colleagues to be able to improve their predictions to match our data. Finally, for this analysis, we actually use the B-tagging information. And so here you're looking from loose to tightest B-tag to define categories. And what that actually allows you to do is to have control regions in the analysis to actually be able to check various aspects of the modeling and to make sure that when you're making these corrections and going into the signal region, that they actually describe the data very well. This slide, I think something went wrong here. I'll fix it online. But what I want to show you is a little bit how we got to BB observation. So I want you to start at the top left here. This is looking at 7 TV with 5 inverse femtobonds of data. That time we had 0.7 sigma expected. Actually, we had a downward fluctuation, so there's no observed written. As we add more data, go up to 8 TV and 20 inverse femtobonds. At this point, we're looking at an expected significance of 2.5 sigma and 1.7 sigma observed, up to 13 TV with 36 inverse femtobonds. Now we're at the 3 sigma level, and the result which has been highlighted today, yesterday, where we had the 4.3 sigma expected and 4.9 sigma observed. And when you put everything together, looking from 7 to 13 TV, and combining all the different BB production modes, you end up with an observed significance of 5.4 sigma and 5.5 sigma expected. And so I think it's kind of nice to see how this actually evolved as we ended up getting more data and also improving our analysis techniques. So far, I've been talking about Higgs coupling to quarks, but I've only been talking about the 3rd generation. And of course, if you look at the Yukawa couplings, there's already a rich flavor structure. And so some of us were wondering what would if we're actually able to probe the 2nd generation quark coupling using CHARM. So what we did is we did an analysis using an analogous strategy to VHBB, but simplified. We only used the 2-lepton analysis, and instead of a BDT, we actually fit the dijet invariant mass of the Higgs candidate. Now, the crucial element of this analysis is actually to be able to tag CHARM jets, and here we really profited from having the IBL, which significantly improved our detector performance. So in the plot here, this is actually showing you how we do the CHARM tagging. What we do is we actually train a BDT where we look at B versus CHARM jets, and also CHARM jets versus light. And we make a cut in the 2D space to decide what we want to call CHARM and what we want to call background. And the working point that we end up getting has a C-tagging efficiency of 40%, with a 4 times rejection for B quarks and 20 times rejection for light quarks. So putting this all together, this is one of the final distributions of the analysis. Where we are right now is at 100 times the standard model. This was with 36 inverse femtovans of data. And it's actually the strongest direct limit we have on the Higgs coupling to charm. More recently, there's actually been a projection for the high Lumi LHC, which suggests that we might end up getting to something like 6 times the standard model, again with a simplified analysis. So it'll be very interesting to see how this might evolve. So in conclusion, I think it's been, at least for me, exciting 10 years since the start of the LHC and 6 years since the Higgs discovery. And I think that excellent detector and software performance has been key to many of our important physics results. This summer has been particularly exciting for me on a personal level because we've been able to observe the coupling of the Higgs to quarks via its interaction with both top and bottom quarks. So far, we see that the results and the Higgs sector in general are compatible with the standard model, but I think that observation is only the beginning. And I'm very curious to know what we're going to learn about nature from the future LHC data. Many thanks to all my collaborators who, of course, made major contributions to all these works. Thank you.
Thanks, Heather. We have time for one question. Okay, if not, let's thank Heather again and congratulate her for the work. So next is the awards session for the posters for ICHEP, and Young-Jun Kwon is going to present the awards.
Let's have a Best Poster Award ceremony. And the award winners are selected by the program committee, composed of Sung-Yeol Choi, Soo-Young Choi, and myself. So there are about 240 posters which you all enjoyed and participated. And the next page. Okay, so this is how we did the event selection in terms of the high energy physics language. First, we used the variable, the judgment. And these people have contributed to the judging process, and I really thank you. I mean, the program committee really thank you. And then the second variable was the popular vote. And we did multivariate analysis of this J variable and, J variable and the P variable. And we did a blind analysis, and we only handled the poster ID without name, without title, without affiliation, and we used some undisclosed magic formula. But we did not use machine learning for that. Okay, then here are the third prize winners. First, there is Moses Chung from UNIST about measurement of phase space density evolution in mice. Do we have Moses Chung here? Could you stand up? Yeah, stand over there. And next is Jun Lee, Jeonbuk National University, about performance of the Koto sampling calorimeter. Do we have Jun Lee? Yeah. So could you please come to the front? And we have Christoph Alt from ETH Zurich about data reconstruction and analysis for the 311 meter squared meter cube dual phase liquid argon time projection chamber prototype. So do you have Christoph? So could you come front? And the final third prize winner is Arindam Das from KIAS about heavy Majorana neutrino pair production at LHC in minimal U1 extended standard model. So do you have Arindam? So could you all come to the front so that people can know who you are? So please come on the stage. Okay, so these are the proud people. Let us give big applause to these third prize winners. And to save time, because of your lunch time, please pick up your certificates and prize money at the registration desk, which is just outside. Okay? Thank you very much. And let's big applause again. Yeah. Now we move to the second prize winners. The second prize winner is Chayanit Asawatang Trakuldi from DESI about searching for additional Higgs bosons in final states with B quarks with the LHC run-2 data at CMS. Could you come up on stage, please? So, Best Poster Award, second prize, title, Search for Additional Higgs Bosons in Final States with B quarks with the LHC run 2 data at CMS. In recognition of the achievement in the poster session at ICHEP 2018, this award is presented to Chayanit, Asawatang Trakuldi, Deutsches Elektron and Synchrotron. Okay, then next second prize winner is Stephen Schramm, but unfortunately, he is now in the airport, so he cannot enjoy this ceremony. But anyway, he's from University of Geneva, and his poster is about triggering on hadronic signatures in Atlas. And finally, the first prize winner is Jesse Liu, Oxford, about innovative strategies in the search for electroweak production of compressed SUSY states with the Atlas detector. Jesse, are you here? Yes, please come up on stage. Okay, so Best Poster Award, first prize, title, Innovative Strategies in the Search for Electroweak Production of Compressed SUSY States with the Atlas Detector, in recognition of the achievement in the poster session at ICHEP 2018. This award is presented to Jesse Liu, University of Oxford. And before the poster presentation, poster showcase, all the prize winners, could you please come up on stage? We'll have a big photo. Okay. So please come up on stage. Third prize winners, second prize winners, together. Thank you. Congratulations. And now I will disappear from the stage, and there will be a poster showcase by the two second prize winners and the first prize winner. Okay.
Hi everyone. I'm Chayanit from DAISY, and on behalf of the CMS collaboration, first I would like to thank the conference organizers for organizing such a great conference here. And thanks to the CMS collaboration and everyone who likes my poster and voted for me. So on my poster, I was presenting the search, one of my work with DAISY and CMS collaboration on the search for beyond standard model Higgs bosons decaying to the BB bar pair using the 13 GeV data collected by the CMS detector. So the motivation of this work, we focus on the beyond standard model theories, especially for the two Higgs doublet models and the minimal supersymmetric standard model. And we found that our sensitivity, our analysis is sensitive to the type 2 of the two Higgs doublet models and the flip models. I will not go into much details here about theory, and I will just move to the next slide. So this search is so far the unique analysis at the LSC, and we look for the BB bar channel, because it's the dominant decay channel in the large parameter space of the MSSM and two Higgs doublet model. And then we also enhance the sensitivity further with the B-associated production, as you can see from the Feynman diagram at the tree level here. So during the data taking, we have developed the dedicated triggers to require two online B-tag jets. And you can see from the diagram that we have many B jets in the final state. So one of the main challenges from this analysis comes from the large QCD multi-jet background. So we also develop the data-driven parametric approach in the control region to model and estimate this main background. And after we collect data from our trigger, then in the offline selection, we require event to have at least 3 leading jets, B jets to be B tagged. And as you can see from this event selection, the first 2 B jets most likely to come from the Higgs candidate, and the third B jet is supposed to be the B associated production. And at the end, we reconstruct our signal from the invariant mass of these 2 leading B jets, as you can see from our signal shape here. And we interested in the mass range from 300 to 1300 GeV mass range. And this plot shows the signal efficiency of after each selection, and after all selection is the red curve here. And the signal efficiency ranged from 0.5% up to 1.4% at around 500 GeV mass point. And as I already mentioned that our main challenge also from the QCD background, so we use analytical function that we developed in the control region for the blind analysis. And we found that QCD multi-jet background is well described by Novosibirsk style functions. We also introduced the subrange division to help us reduce the uncertainty from the background bias. And from this analysis, the systematic uncertainties dominated by the trigger efficiency, B-tagging efficiency, and the background model bias. And finally, we perform a maximum likelihood fit to the invariant mass of the 2 leading B jets distribution, as you can see from this curve. And you can see that the data is well fit by the background model, so no significant excess is observed along this mass range. So we compute upper limits on the cross-section times branching fraction at 95% confidence level, as you can see from this plot. And from our analysis, now we achieve the best sensitivity in this channel to date. And you can see the sub-ranges is the effect from our sub-range division method. And then we interpret our cross-section limits into the exclusion limit in various MSSM scenarios. For example, this plot shows the MH mod plus scenario of the MSSM, and we compare our sensitivity, our results with the run 1 results from 7 plus 8 TeV, and you can see that we already achieved better sensitivity compared to run 1 analysis. And then we interpret our limits into the exclusion limits on the parameter of the tangent beta and cosine beta minus alpha, and for the mass of the boson. In the context of 2HDM flip model, and also the type 2, as I already said, that we sensitive to these 2 models. And we provide a unique limit for the low cosine beta minus alpha of the flip model, as this region is the most, where the Higgs coupling is the most like standard model-like. And we also provide, and this result is the complementary to the analysis of A decay to the ZH measurements, as you can see from these 2 plots. So this is what I was presenting on my poster. Thank you.
And the second prize winner, Stephen Schramm, has video recorded his acceptance speech. So could you play the video?
To be here and to receive this. I'm sorry I can't actually be physically present. I'm on my way actually to the airport right now. Okay, so brief introduction to what my poster is about. It's about hadronic triggers in Atlas. And what I mean by that is anything related to jets, missing transverse momentum, or B-jets. So in general, we have 2 stages in the Atlas trigger. The first one is hardware-based, where we have to take our 40 megahertz collision rate and reduce it to about 100 kilohertz. And then the second stage, after we have done this hardware selection, is to reduce it to a final 1.5 kilohertz using a software trigger. So these are the 2 primary stages, and that's for the entire Atlas rate. At the first stage, about 1/4 of it is for jets missing ET and B jets, and at the second stage, roughly 1/4 to 1/3. Okay, so it's important to briefly discuss each one of these stages. So the level 1 stage, we don't have the time to read out the entire calorimeter. So instead what we do is we take projective slices in the calorimeter, And by that I mean we take, there's several cells in each layer, and we take just one big readout of the entire calorimeter projection. And then we take 8 by 8 of these, so a 0.8 in eta by 0.8 in phi, and we scan across the calorimeter using this information to find a local energy maximum. And if this passes a threshold, then we say that this event has been selected for example, a jet. And if it does not, then we say it has not been selected. After that, we go, this is our level 1 hardware decision, then we go to something more complicated, which is we read out the entire calorimeter exactly as we do offline, and we form what we call our topological clusters. And these are noise-suppressed clusters, so we only read out the energy if there's some significant energy deposit. And then we use these as the input to jets. And jet building is performed very similarly to offline, and there's been substantial improvement since 2016, where going from 2016 to 2017, we changed our calibration procedure, and we also did a 2-stage selection. So first we build the jets, we have some loose cut, and then we build tracking information, and we feed this back in, so that we can improve the calibration even further. And then once we have improved the calibration, we have something which is nearly a step function now, which is quite a significant improvement over the past, which was a very slow resolution timeline. So after you've built jets, you can also say, is there a B jet in the event? And so the same type of thing is done. We first have a first pass on the jet selection, and then a second pass where we run tracking information, and we calculate multivariate discriminants, very similar to what we did offline. Again, between 2016 and 2017, this was substantially improved. So our B-tagging information, if you apply exactly the same cut in the trigger and offline, is typically within about 5% and stable across pileup. So this is great performance. Another thing you can do with jets is you can feed this into calculating missing ET. You just take all of the jets in the event, you sum them up, and you say, well, whatever energy is energy imbalance remains, this is a lack of energy, and this is potentially an indication of invisible particles. So if you do this, this is what we did in 2016. It works well, but unfortunately, it has quite a strong pileup dependence. So in 2017, we developed a new algorithm where we fit the energy distribution in the calorimeter. And by fitting that energy distribution, we can subtract all of the soft, well, we can veto all of the soft energy and subtract all of the hard energy. And then that means that we have a much better estimate of the missing ET from the actual hard sources, and we also suppress the pileup drastically. So this takes our rate for missing ET triggers from something which is exponential to something which is quite linear. And that's a huge improvement, and we also find that it improves the trigger efficiency, so we don't lose anything. The very last thing to discuss briefly is large R-jet triggers. So if you have a W or top, and this decays hadronically, this is now into 2 prongs or 3 prongs. But at high energy, these are boosted and they're all overlapping with each other. So there's 2 things that we did to improve this. The first is at level 1, we actually have a new piece of hardware called the topological trigger, which takes different 0.8 by 0.8 windows that I spoke about and merges them together into one larger window. And so that reduces the dependence on having 2 corks instead of, that don't fit inside one of these windows, they fit in 2. And then the second thing is at the high level trigger, the software trigger, what we do is we take advantage of the fact that a W boson or a top boson are similar, have a real mass, where QCD doesn't. That means that at low mass, your QCD is peaked around 20, 30, 40 GeV. So a 30 GeV cut on the mass is fully efficient for all of your signals, but it kills about a factor of 4 of all of your background. And so this is, using this, we can suppress the rate by a huge amount, and we can reduce the thresholds of our triggers for large R-jets by 50, 60 GeV, which, given that it's an exponentially falling distribution, this is quite a bit. So that's it. Thank you very much again. This is a great pleasure to have received this award, and yeah, that's it. Thank you.
So hi everyone, it's a real honor to have received this award, and so my poster was about some new ideas in Atlas that we were pursuing and have deployed to probe the compressed frontier of electroweak SUSY searches. So on the left-hand side you can see a sort of cartoon of what we are trying to look for in our detector, the transverse plane. The orange jets are, you have this one energetic jet which boosts your invisible particles. Those are your 2 dashed lines there. And the 2 blue lines are the soft leptons, which I'll discuss in a moment. Okay, so the backdrop to this story really was that even as recent as last summer, we were extending our sensitivity to these new charged or neutral fermions along the x-axis, the masses, all the way beyond 500 GeV as a function of the dark matter mass on the y-axis. So these decay into gauge bosons, as you can see on the Feynman diagram. So, and what is perhaps very striking is that the cross sections in about 100 GeV, you can see along this boxed area that I've circled there, are about tens of picobarns, meaning that we can produce about 500,000 of these events in just a year now. And we have no sensitivity in this region there. So we could be completely missing supersymmetry in these very high rate cross-section. So this region is also theoretically favored. These are the regions where we expect Higgs-zenos, Higgs-zeno dark matter, to be near the weak scale for naturalness arguments. And the key principle here is that the mass separations between the states, this multiplet of charged and neutral states, are expected to be about 1s to 10s of GeV in mass separations. And at the LHC, it's an extreme challenge to reconstruct, let alone even trigger, on the very soft decay products between these states. And so one of the performance highlights we had to do to confront these soft lepton reconstruction limitations is extending all the way down to 4.5 GeV or 4 GeV for electrons and muons. So you can see the efficiency is a function of lepton PT there for muons in red, electrons in blue. And sort of a fun fact is that muons lose about 3 GeV of energy before they even reach the muon spectrometer. Right? And so that's why we're really confronting some detector limitations here. So why do we need even these soft leptons, right? Why is the monojet plus MET signature not sufficient, right? It's because we need this powerful background discrimination that you get when you form this dilepton invariant mass along the x-axis. So you can see the solid colors there, the background, and the dashed lines are your signal, right? And it's sort of a shame that, yes, we didn't really see any data points rising above the background at low values there. So the sensitivity that we have, right, so this is now zoomed into that little boxed region at the beginning here. So the x-axis is now the mass of that charged state and the mass separation on the y-axis there. So notice the log scale there, right? The gray region is the sensitivity excluded by LEP, and you can see our success story, right? The soft lepton search in blue is the first hadron collider sensitivity to these dark matter, Higgs-zeno dark matter scenarios beyond LEP. Now, as the mass separation becomes smaller, what happens is that the phase space becomes so small that the charge unit becomes long-lived, and it actually leaves hits in the pixel detectors there. Right? So this is the disappearing track search, which is the orange region there. So this is a real complementarity between the prompt soft lepton searches and these long-lived disappearing track searches. And so we're left with this picture now. How do we close this gap between the prompt and the long-lived for these Higgs-zeno dark matter scenarios? Can we use softer leptons? There was actually a nice poster on this to push downwards. Can we use shorter tracklets to push the disappearing track upwards? Right? And this is really underscoring the fact that we need new experimental ideas. These are detector limitations to discover these Higgs-zeno dark matter scenarios, perhaps even below 100 GeV there. And that's where I'll leave it. Thanks very much.
So thanks to all the speakers and congratulations to all the awardees. So with this, we close this session.